and then minus y when to redistribute the partial z, that's going to become xfzz minus partial xf or fx minus z fxz minus x, and then we distribute that, and that's going to become partial yf plus z. Okay, that's going to become fyz. Oh, and there's another term in there. Minus y fzz plus z zfxy minus y fxz. There we go. So now let's try to condense that even more, right? So first things first, let's bring all the z terms together. So we're going to get minus x times fy plus z fyz minus y fzz minus y x fzz minus fx minus z fxz, and then you add the z terms together, and xfyz, oh sorry, minus z fxy canceled out with no. So we have z times, where's the other z term? Oh man, oh, here it is, okay. So minus z fxy cancels out with zxfy, fxy, and we have left over xfyz minus yfxz. There we go, okay. So then, what else is left over? Well, now let's refactor this. Factoring out fyz first, because that's the first thing I see here. We have xz minus xz, which means it disappears. Then the next thing I see is fxz. There's a minus yz term right there, and there's a plus yz term, or minus y times minus z, which is a plus yz term over there. So that also disappears. And then plus fzz, well, there's a xy term over there, and there's a minus yx term over there, so that also disappears. And, well, everything else is minus xfy and yfx, so it's yfx minus xfy. So at the end of the day, the commutator of lx ly times x and equal to minus IH bar squared times. I know. I'm just trying to write an important result. Y partial xf minus x partial yf. There we go. So now, what do we do with this? Well, you probably have noticed that this looks very similar to, if we eliminate the f, that makes it look more like this, which is very similar to LZ, which is just minus IH bar times y partial x minus x partial y. There's so, well, what are we left with? We should get minus IH bar LZ. There's a sign error here because I'm supposed to be getting IH bar LZ, but whatever. So by cyclic permutation, you can probably realize that the commutator of Ly Lz is going to be I(h bar Lx, and Lz Lx is going to be I(h bar Ly. All right, now we're just getting started. So, don't want to crack my fingernails over here. So, over here now, we're going to realize that this means Lx and Ly, well, the standard deviations of them, when we measure them, they're going to have to be at least, their product is going to have to be at least 1 over 2I multiplied by minus I(h). No, it's not minus. Oh, sorry, yeah. So it's going to be equal to the absolute value of 1 over 2I minus I(h bar Lz. So, at the end of the day, it's saying that it's going to be greater than or equal to h bar over 2 Lz. Oops. So that means that these two are not compatible. And the same thing happens with Ly and Lz. They are going to have to be greater than or equal to h bar over 2 Lx. So, and we'll see soon the intuitive reason why if Lz is equal to 0, we can perfectly know both Lx and Ly very well. 2D things are always the best, except for life. Life is better than 3D. So, now we want to search for something that is compatible. And the natural next best guess is, what about the magnitude? But of course, the magnitude by itself is messy. What does it even mean to take the square root of a bunch of operators?